Hi everyone, my name is Arpita Vats. I am a PhD student at Santa Clara University. Today I will be presenting my paper on enhancing retail checkout through deep sort object tracking and YOLO V8 detection. We all know that AI and computer vision technologies are revolutionizing the way we shop and check out in the retail store. Today I will discuss how AI and computer vision are gaining popularity in the retail industry, the increasing prevalence of self-service option and specific focus of Track 4 in the 7th AICD challenge on automated and accurate checkout system. Track 4 AICD challenge specify the focuses of the computer vision development in the area of retail checkout. In this work, we introduce innovative framework named Retail Counter, one that incorporates a video in painting alongside detection, tracking, and selection module for accurately reporting the count of unique item observed in the video. Teams were furnished with a training data set comprising both genuine and synthetic images totaling 116K500 item scan along with associated segmentation mask. The testing data set includes numerous video clips with clips featuring one or more complete scanning action performed by customer in the natural manner. Multiple customers participated, each with slightly varied scanning pattern, thereby adding to the complexity of the experiment. A shopping tray was provided for the placement of scanned items in the test scenario, while the camera was positioned overhead and aimed straight down at the checkout counter. Automated checkout system faces various challenges in a real-world scenario that can make the process difficult. Factors such as object occlusion, motion, and item similarity can pose challenge for accurate item recognition and detection. Object occlusion refers to instances where items are partially hidden or obstructed, making it harder for the computer vision system to identify and differentiate them. Motion can introduce an additional complexity as item may move or be repositioned during the checkout process, requiring a robust tracking and detection algorithm. Another challenge is item similarity, where products within a similar appearance or packaging can be challenging to distinguish accurately. The real world factor requires advanced computer vision techniques to overcome the challenge they present. The introduction of new seasonal product adds another layer of complexity to automated checkout system. Our object detection model was developed using synthetic image generated from a 3D scan object models and their corresponding segmentation masks. Owing to the limitation on external dataset uses, we produced a background that resembled the tray color in the test video and incorporated Gaussian noise. To enrich the training dataset, each image featured up to 3 objects from distinct classes. We successfully employed the photorealistic single image superresolution using a generative adversarial network SR-GAN model to obtain a high-resolution images resulting in superior training image quality. In total, we generated 130K training images and 20K of validation images. To train our model, we fine-tuned the pre-trained weights of YOLO V8, which is currently acknowledged as the state-of-the-art model for object detection. This is an example of how our dataset looks like. This depicts our framework, which we will be discussing in the next section. As we can see from this diagram, that initially we take the test video, which we extract 60 frames per second, which is followed by a video in painting technique, which helps us remove the outliers, and then we further go for ROI detection, probably which means like the area of reason that we are interested in, and then we pass it to our detection model, that's YOLO V8, followed by a deep sort tracker and the merge algorithm to get the final output, which includes video ID, class ID, and the frame position that object came into the frame. During training, these products were isolated in the frame and placed in a free space without any other object in close proximity. However, during inference, the model sometimes detected the worker's hand or body as a false positives, even when no products was present in the scene. To tackle this issue, we employed a computer vision technique to first detect human body parts, particularly hands, in the given frame and generate a mask to represent their location. This involved using key point detection method to estimate the position of hands, semantic key points, or identify the hands as object respectively. Subsequently, we applied a flow-guided video in painting technique, which utilizes 3 trainable modules: flow completion, feature propagation, and content hallucination, to jointly optimize the painting process. Our proposed method yielded superior results both qualitatively and quantitatively, outperforming the state of art technique and demonstrating promising effectiveness. Since the primary goal of the challenge was to identify objects solely above the white tray, we decided to dynamically identify the bounding box of the tray as our ROI and limit the detection and tracking within that region. To extract the region of interest, we used an OpenCV MOG2 library to extract the background and foreground of the image. In the given frame, the background image was converted to grayscale, and a SCAR operator, which is an enhanced version of the Sowell operator, was employed for edge detection. The SCAR operator was executed in both x and y direction and then combined. The largest rectangle in the frame was used as the region of interest, named as white tray, as depicted in the figure here. The proposed method is a multi-step approach in our proposed system. Frames extracted from the test set A are utilized as an input. The frames undergo pre-processing in the first step, which result in cropped and masked frames. The second steps involve passing the proposed frames into the detection network, which generates location bounding boxes. The frames that have location information are then fed into deep sort and the classification network, producing the tracks with a category score. The final step involves using a merge algorithm to fine-tune the object tracks and select the item output frame for each track. Our primary objective was to assess the effectiveness of each approach, identify the best performing combination. We evaluated the outcome based on the specific metrics such as accuracy, precision, recall, and F1 score. After a thorough evaluation, we found that YOLO V8 detector model paired with a deep sort tracking method yields the best result in our study. This combination achieved an impressive F1 score of 0.817, indicating a high level accuracy and performance. Our model's performance in the competition is a testament to the rigor of our experimentation process and robustness of our object detection pipeline. To obtain this positive performance, we conducted extensive experimentation using different object detection methods and tracking algorithms. Using this proposed method, we were able to achieve fourth position on the public leaderboard with competitive result, which utilizes YOLO V8 detection and a deep sort tracking algorithm. Thank you.